have a value 6. Doesn't that nail down exactly which one we're talking about? Isn't there only one of these family members that goes through that point? Right? So that allows me to identify exactly which one I'm talking about here. And once I have that, what can I do? Go back again, and it's going to give me a family again, right? So now I get another family of functions, and I give you one other piece of information. The original function at 2 is 4, right? So that means at 2, you should be up here at 4, and that allows me to nail down exactly the one we're talking about. Does that make sense to you? That we have to have this information. If we don't have this information, we cannot get back to f of x and get a unique answer, right? Okay, let's do the actual work. No questions on the pictures? Sure? All right, so let's first go back the first step, from here to here, right? From here to here. So the first derivative, which is what you get when you go backwards from the second derivative, should be the antiderivative of this. So what's the antiderivative of this? 6x squared, right? Now I'm just doing that. You can check, use your power rule, right? You should get 6x squared. Do y'all feel like y'all could get that? Okay, 6x squared plus c. We don't know what the constant is. So now what we're over here, we've got this family of parabolas, right? This family of parabolas. We're trying to figure out which one it is. So now I use this right here. So I'm going to say, but f prime of 1 must equal 6, which implies that when I plug 1 into this, right? When I plug 1 in right here, I should get what? 6, right? Oh, that's kind of boring. What is c then? 0. The c is 0, which implies that c is 0. Just solve that. That's just a little linear equation, right? 6 plus c equals 6. Subtract 6 on both sides. C is 0. Right? So c is 0. That tells me that my first derivative is just the 6x squared function. I know that exactly now, right? I know exactly what the first derivative function is. And now I'm just going to go again, right? Go backwards one more time. So I'm in where am I doing it? I'll squeeze it in right here. So the original function should be the antiderivative of this. So I'll write it down this time. Bring the 6, power rule, 1 over 2 plus 1, x to the 2 plus 1, plus a constant, right? I'm not going to use c twice in the same problem. I'm going to call this d instead of c, just so that we don't confuse the two. So what do we get there when we simplify that? 2x cubed plus d, right? Plus d. Now I almost know, right? I almost know what f is. I've got the family. It's a bunch of cubic functions. So to find d, I'm now going to use this information right here. So, but, I'll squeeze it right in here. But f of 2 equals 4. But that implies that when I plug 2 into this, I should get 4. So 2 times 2 to the third plus some d I don't know must equal 4. D is negative 12. D is negative 12. Yeah, that left side, 2 cubed is 8 times 2, 16. Move it over, subtract it, you get negative 12. So that gives me my final answer, that the original function must be 2x cubed plus 12. Minus 12, thank you. Minus 12. There we go. So that's something you should be able to do, right? These two pieces of information have a name. They're conditions, all right? They're just conditions that are given. So you're given some information about the second derivative, and you're given two conditions, right? If this number is 0 and 0 here, then we call them initial conditions because it's what's happening at, you almost look at the x values like time. And so you're saying like at time 0, here's what's happening. So we refer to those as initial conditions. Here, I didn't give you initial conditions, I just gave you conditions. All right. What were they, 2 and 1, right? Okay. All right, feel okay with that? All right, so the next thing I want to talk about then is just, I want to tie this to something that you may or may not have seen already, and that is this formula right here. Maybe I should back up. Recall from Cal 1 that if d of t is a linear displacement function, or if you want to call it a position function. So if somebody gives you a function, I'm going to call it d of t here. D stands for like distance, t is like time, all right? If somebody gives you a position function in Cal 1, then what does the derivative of the position function give you? What is the derivative of position? No? It gives you the speed or the velocity, right? So the derivative gives you a new function called we'll call it v of t, which is the velocity function. This is really important in physics. If you have a position function, the first derivative of that position function gives you the velocity function. So it tells you how fast that object is going at every point in time. How many of you now remember that? Yeah? Yes? Okay. Yeah, so we need to be able to remember that connection. Position, take derivative, get velocity. What if I take derivative of velocity? I get acceleration. So if I take the second derivative of position, or if you want, that's the same as the first derivative of the velocity, that will give you the a of t, which is the acceleration function. And that's for everything. In Cal 3, we have the same things, but we're dealing with things that are moving not in a straight line. See, here we have linear displacement, which means things moving in straight lines. But in Cal 3, these things are allowed to move in 3-dimensional space or even higher dimensional space. These things still hold. Derivative is velocity, second derivative is acceleration. What is the difference between velocity and speed in a linear? When you have linear motion, is there any difference between velocity and speed? If it's linear motion, like if you're moving in a straight line, is there any difference between velocity and speed? Velocity, hold on. Velocity is like the total and speed is like the opposite. Velocity is both a direction and a speed. Velocity is a vector, okay? So when you're in a straight line, it really is no different than speed. So that vector, and this isn't a class where we're teaching vectors, okay? But for this, again, physics. A vector has a length and a direction, okay? This function right here, this velocity, for us in this class, it's just the length of that vector, all right? But in a Cal 3 class or physics, you also take into account the direction of the motion. So I'm just wondering if anyone knew the difference. Velocity and speed are not the same thing, generally. Velocity is a vector, the speed is the length of the vector. All right, so we've got position, derivative of that gives us velocity, derivative of that, second derivative, gives us acceleration. Now, the reason I'm bringing that up and how it's tied to antiderivatives is this. Let's see by a show of hands how many of you have seen this formula. D of t equals negative 16t squared plus v naught t plus d naught. This is a physics, no? Kinematics, have you seen that? Yes? So this is a formula that will calculate if you're on Earth, if you drop an object, it will tell you exactly how high that object is off the ground after a certain amount of time has passed by. If you take out air. So if there's no air, this will tell you exactly where something is, right? I hope everyone knows that on Earth, all objects will fall at the same rate regardless of their weight. Doesn't matter if you have a feather or a bowling ball, they should fall together if you take air out. You put air in, yes, there's going to be a problem, but this is the formula that calculates that if there was no air, okay? And I know that you'll sit there and go, but there is air. Well, then the formula becomes more complicated, but you got to start out with the basics, right? You got to crawl before you walk, or no, crawl before you walk before you run, right? So this is like we're crawling just to understand how things work. Where does this formula come from? I'll show you, all right? We're going to derive it. It's very simple. We're going to go backwards, okay? We're going to try and get to the d of t function. This is the v of t function, the velocity, and here's the acceleration function. If I take an object on Earth and I let it go, it just starts dropping, right? Due to what? Gravity, right? And gravity is a force, right? Is gravity a force? Gravity there's an acceleration, right? And it's constant on Earth. Does anyone know the acceleration of gravity? 9.8 meters per second. Y'all have heard that before? If we convert that into, instead of meters per second, if we convert that into feet per second, it's approximately 32 feet per second. That's the acceleration of gravity on Earth, all right? So that means that our acceleration function is the constant 32. And actually, let's go with negative 32 because we're going to look at it as going down is going to be in the negative direction, going up is positive. So negative, right? Normally in physics we say negative because we have to, everything's relative, right? Like if I throw a ball to you, is it going away from me positive, or is it, like what's our axis? You know what I mean? So we orient downward negative, upward positive. Do you all agree that the acceleration function on Earth is a constant? What's the antiderivative of this to get to velocity? So what's the antiderivative of a constant? Not derivative, antiderivative. Negative 32x, right? But in this case, what's our variable? T, right? So we're just going to say negative 32 t plus what? Some constant I don't know, right? Okay, I'm put c. Let's keep going. I'm not going to be able to nail down c, am I? Let's take the antiderivative again. So what's the antiderivative of this? So bring the negative 32 over. I'll do it right here. Now we do what? Antiderivative of t would be 1/2 t squared, wouldn't it? And what does that give you? Negative 16 t squared plus, okay, what's the antiderivative of a constant? The constant times the variable. Here the variable is t, so ct plus some other constant, which I'm not going to call c, I'm going to call it d. Okay, do you all see we have the formula already? That is the formula, with one little exception. Here, we call this v naught. This is always the starting velocity of the object. Now let's see, what is it over there for us? It's c, right? So where are they getting that from? Look, what if I told you right here at this velocity, what if I asked you, hey everyone, what's the velocity at 0? What would you tell me the answer is? C, right? So this number is the velocity at time 0. All right, now look at this function. And I say, hey everyone, what's the position at 0? What happens at 0? If I plug 0 into this, what do I get? D, right? So this is what we call D0, which is your starting position. And that's where this comes from in the formula. In this formula, that's always your starting velocity, and that's always your starting height. Do y'all see it's just a simple application of antiderivatives? Simple application. In fact, if you go to a different planet, right, moon, this changes, right? That's the only thing that changes on the moon. The acceleration of gravity is different. But the position of an object dropped on the moon will be modeled by a what function? What type of function is this? Quadratic, right? And wouldn't that happen for any mass, any object that had gravity? Is that any object that has constant gravitational acceleration should have a parabola that models any object moving through the atmosphere on that. Does that make sense? Or being dropped, I should say. So parabolas are uniquely the perfect model for gravity, for modeling falling objects on any planet. That's pretty cool, right? I mean, the math shows that if you start with a constant here, you're always going to get a quadratic, right? Always. Because you have to go twice. You have to go back twice. Each time you go back, you gain 1 power on the variable. Okay, that was just to show that. How much time? 15. Y'all doing all right? Y'all look tired today. What's up? That's all right. I mean, long weekend. Yeah, yesterday felt horrible for me. But we still got time, and you already had a holiday, so we got to crank this out all the way to the end today. All right, we are done with 4.7, antiderivatives. There's still probably some overlap here, but this class, the beginning of next class, will probably be where the overlap starts to end for a lot of you. We start to get into newer material. So quickly, notation. It was very simple in Cal 1, it was very simple if I wanted to tell you to find the derivative of something, right? I would just be like, find f prime. And then you would know what I mean, right? Find the derivative. We need a special notation for finding antiderivatives. Something where I can write it down. You know that what I'm looking for is the antiderivative, right? So here's the notation. If we write down this, right? And I'm trying to think of how I want to say this. If we write this symbol down, and then I write little f of x in here, and next to it I put dx like that. What this means is that you need to go find me the antiderivative and add a constant to it. So this notation right now is not going to make a whole lot of sense until after, probably a month from now, I will get into the details of why we use this notation, all right? Maybe not a month, maybe like 3 weeks from now. I will tell you like in detail why this symbol is what it is and everything else. For now, I want you to look at this symbol as an instruction. This symbol right here, which is called anyone know what that's called? The integral sign. Look at the integral sign as a stretched out, elongated S. It's like S stretched out, okay? It's like you grab the top and bottom, and you rip it out like that, and you become this, right? And it actually does have something to do with a sum, which we'll get to later, right? There's something called the Riemann sum. The integral sign, right, is an instruction to you, hey, you got to go find the antiderivative, right? Of what? This right here. That right there, that function is called the integrand. The integrand. It's kind of like with a radical. The thing underneath the radical was called the radicand. I don't know if you remember that, but that was called the radicand. This is called the integrand. And the dx is the part that's going to be the most difficult for me to explain to you. But for now, we're going to call this the differential. The differential. That did not spell that right. Differential. I think I got that right. The differential. And I don't want us to get bogged down. This is one of the most confusing things for students because I haven't explained all the geometry behind where this is coming from, which I will later. So for now, what I want you to look at this is this keeps track of your variable. Keeps track of the variable and chain rule, as you'll see in a minute. Keeps track of the variable and chain rule. So what that dx is telling me is that I'm trying to find the antiderivative of this function, and yes, indeed, x is the variable in this problem. X is the independent variable. In Cal 3, you might have a problem like this where you have an integral, you have f of x here, and this might say dy, which means that you're treating y as the independent variable, which is different. So it just keeps track of things for us, right? It's kind of like the difference between if I write y prime versus dy dx. This is called Leibniz notation. How many of y'all saw Leibniz in Cal 1? You should have seen Leibniz, right? This is just our standard notation for derivatives. The advantage to this is that you can tell what you're differentiating with respect to. Here you're differentiating with respect to x, the lower variable on the bottom. Here, yes, you know you need to take derivative, but you don't truly know what you're differentiating with respect to. You're assuming it's x. My former students, you remember my story about the club and the girl, the question, right? Differentiate with respect to. Very important thing, yes? Okay. All right. So that's the notation. So let's just use that notation real quick. Let's start with the first problem we had today. What I'm asking you to do here is find the antiderivative of 2x, right? And what is the antiderivative of 2x? X squared plus a constant, right? That's it. You're done. It's just another way of me asking you that question. So you're really just, aren't you really just looking at this right now? Like you're just looking at that and saying, what's the antiderivative of that? And you get this? Students will always ask me, well, what happened to this, right? What happened to that? Well, you're not looking at that, right? You're looking at this, and that's what you're finding the antiderivative. This is just telling you what the variable is. Yes? No, well, I said if you're really having a problem, if you really need that to go somewhere, right? Like in your mind, if you need that to become something or something happened to it, then you can use it to help you remember plus c if you want. But technically, that's not what's happening. All right, so every problem I did today, I could have just done with this, right? Integral sign in front of it, little dx in the back, and you would have got the same answers, yes? Okay. So with that in mind, let's now try this. So I'm asking you right now to kind of forget that's there, find me the antiderivative of this, right? What's the antiderivative cosine 4x? Hold on, my wife's about to get on a plane. Yep, okay. So antiderivative of that is what I'm asking for. So your first instinct is probably, okay, well look, it's cosine, right? The antiderivative of cosine should have something to do with sine, yes? And I think a good starting point for a guess on this would be sine 4x, right? I mean, let's just guess. I'm taking kind of a guess here. Is that right? Does that work? So this is more of a question. It does not work. Why? What's the derivative of sine of 4x? Cosine of 4x times 4. Where's that times 4 coming from? The chain rule, right? You'd have to do chain rule. So if you take derivative of this, you get cosine of 4x, then times 4, and we don't have a times 4 here, right? So we're off by a constant, aren't we? We're off by a constant. Like this almost works. The 4 that would come out of this when I did the derivative, right? The 4 that would come out, I would need to kill it, right? So how could I kill that 4? Multiply this by 1/4, right? And that would scale it out. So if I stuck a 1/4 out in front of this, now that would work because this constant's attached to this. So I take derivative of that. Derivative of that would be cosine of 4x times 4, and then I hit it with a 1/4 that kills off the 4, and I get back this. Y'all see that? Yes? Yes? Okay, this is your first example of a problem where we can do it using a method called U substitution. All right, and this is a very basic problem. We could do this without actually doing the process of U substitution, but I want to show you U substitution with this problem. So I'm going to start the problem over. This was just a mental kind of guess and working it out. Instead, I'm going to do this thing called U substitution. This is our first method of finding antiderivatives. In this class, there are going to be 5 methods. Not formulas, methods, what we call techniques of integration. The first method is U substitution. The second method is integration by parts. The third method is trig integrals. The fourth method is trigonometric substitution. And the fifth and final technique is called partial fraction decomposition. Those are the 5 different techniques of integration we're going to learn. This is the first one. This is the easiest. And if you can't do this, the rest you can't do either, right? Everything is going to build on itself. If any one method is missing, you can't do any of the others. So it's going to build quickly.
Is this 5.5? No.
I'm starting to go into 5.5. I'm going to go fully into it next class. I just want to get you going with the idea in this last 8 minutes. Okay, so I'm going to do this problem not by kind of guessing through it. I'm going to do it a different way. I'm going to go in here and I'm going to say, all right, I know that this 4x, right, is going to cause a problem with chain row. I'm going to get a 4 to come out, right? What I'm going to do is I'm going to make a substitution. I'm going to substitute in here. I'm going to make a substitution. I'm going to replace the 4x with u, all right? I'm going to replace the 4x with u. And then I'm going to try and rewrite the problem, right? So I'm going to try and rewrite. So here we go. I'm going to rewrite it. It becomes integral cosine of not 4x, but what? U, okay? So I've rewritten this, integral cosine of u. Now, this is where this becomes extremely important. See, this is telling us our variable is x, right? What does our variable over here change to? It's changed to u, right? So I need to somehow switch that dx over to du. And I can't just change it. I can't just change that to this. In order to figure out what that becomes, here's what I have to do. I have to take this and take the derivative of it implicitly with respect to x. What do I mean? Take the derivative of the left side with respect to x. Derivative of u with respect to x is du dx. What's derivative of 4x with respect to x?
4.
Just 4. Just 4, right? 4. Like that. That's what we get, yes? That's implicit differentiation. I'm differentiating this equation, right, implicitly with respect to x. So derivative of u with respect to x is du dx. 4 comes for the ride. What's the derivative of x with respect to x? 1. Now, why do I do that? Because, see, this has a dx in it. I want to replace this dx with something. So I'm going to solve this for dx. I'm going to first multiply, treat it like a fraction. I'm going to multiply both sides by dx. That will clear it on the left side, and it will appear on the right side. And then I will divide both sides by 4, or multiply by 1/4. I like that better. Let me move this up here. So I multiply both sides by 1/4, and I get dx like that. Now I can replace it. See, I had replaced the 4x with what? U, right? But now I'm going to replace the dx with 1/4 du. So over here, I'm going to put 1/4 du, right? 1/4 du like that. That's the replacement.
I thought the integrals were supposed to have like a number at the top.
The what?
I thought the integral, the elongated.
Oh, this.
I thought that was supposed to have like a number.
Yeah, that's called a definite integral, and that comes later.
Oh.
Yeah, first we got to do it without numbers, and we're not thinking areas under curves yet or anything like that. That's coming.
Why is it they did 1/4 du and not?
I was trying to solve for dx. So divided both sides by 4, which is the same as multiplying by 1/4. I'm trying to isolate dx, right? Trying to get that by itself. So I multiply it on both sides, then I'm trying to get that by itself, so I divide both sides by 4. I'm not going to write it like this. I'm going to write it with a number out front. And the reason why I want this to be a number out front like this is because my next step is to say this. That 1/4 can come out in front of this symbol, because if I'm trying to find the antiderivative of something and there's a constant in here, the constant doesn't matter. It's just going to come along for the ride. So I'm going to bring it out front of the sign, and now my attention is all here, right? And I can just say, okay, this question is asking for me to find the antiderivative of cosine of u. What's the antiderivative of cosine of u? Sine of u, right? So this will become 1/4 sine of u plus a constant. Notice, from this step to this step, that's where the integral sign went away, and that's also where I picked up the plus c, because I actually found the antiderivative of cosine. It is sine, and the 1/4 just came. Now that's almost my final answer, except that my final answer has a u in it, and my original problem had an x in it, so I need to replace u with what I called it, which was 4x. And that'll be my final result. 1/4 sine of 4x plus c, which is the answer we got earlier just by thinking through it, right? Yes? Okay, so everyone, what happened to it? What happened to this du? Nothing. Again, this is keeping track of our variable, right? So when you're at this point, you're saying, okay, what's the antiderivative? You're focusing your attention on this. What's the antiderivative of cosine of u? Sine u, right? This is just keeping track of the variable. But if you need this du to go somewhere, if in your mind you need it to go somewhere, just use it to replace, use it to remember to put a plus c. But it's not going anywhere. It's just keeping track of your constant.
Could that be any? Could that be any like dt or like? That's just.
As long as these variables are the same, on this step, it's just gone.
So there's no value that's associated with it, right?
That's right. We'll see more of what this represents later, and it'll make more sense. For now, I just want you to kind of, when you get to this step, just give me the antiderivative of this. This integral sign goes away. That du goes away. All right, so we are just, we haven't even really got technically into this section. We're finished with the antiderivatives. We are going to go full speed ahead next week. We're going to come in here and we're going to do substitution, and we're going to start integration by parts as well. So there will be quite a bit. Your homework assignments for next week are going to be pretty heavy. Like, you're going to have to do a lot of problems next week. So do your 4.7 homework, the antiderivatives, see how it goes. Y'all want to do a quiz next week when we come back? A quiz over 4.7? Let's do it. Look, in terms of level of difficulty, 4.7 is way down here. You may as well get a quiz on that as opposed to a quiz on integration by parts, right? Which is going to be a harder quiz. So let's get as many easy ones out of the way as we can. So what I'll do is I promise you a problem directly from 4.7 homework, but